If you look inside the walls of the building you're sitting in, or the structural supports of the bridge you commute across, you'll find a massive steel skeleton holding it all together. Every year, we pull over 2 billion tons of iron ore out of the ground, and a staggering 98% of it has exactly one purpose: making steel. This makes an unassuming rock the primary structural support for modern civilization. Getting it from the dirt to your local skyline is a heavily orchestrated global operation. Most of our iron comes from banded iron formations, sedimentary rocks created when dissolved iron in ancient oceans combined with oxygen from early photosynthetic organisms. Iron itself is highly abundant, making up about 5% of the Earth's crust. But economically viable deposits, where the iron concentration is dense enough to justify the massive cost of mining, are exceptionally rare. This map shows the distribution of mineable iron ore. Notice how the supply is intensely clustered. Western Australia's Pilbara region holds over 50 billion tons of demonstrated resources, and Brazil's Carajás region provides another massive concentration of high-grade rock. Because of this geographic lottery, building a local city requires an extraction process that starts on the exact opposite side of the planet. Extracting those deposits requires tearing open the surface in massive, multi-tiered open-pit mines. The global scale of this excavation is staggering, with operations drilling, blasting, and hauling roughly 2.5 billion tons of usable ore annually. To separate the valuable metal from the waste rock, the raw dirt undergoes a physical process called beneficiation. The rock is crushed, ground up, and sent through magnetic or flotation separators to strip away impurities like silica, leaving behind a highly concentrated iron dust. Since blast furnaces can't process fine powder, that concentrate is mixed with binders, rolled into small balls, and heated. The result is a batch of uniform, hardened spherical pellets. Through this intense physical conditioning, ancient ocean sediment is engineered into a refined industrial product, ready to enter the international market. These concentrated pellets are sent down extensive conveyor systems and loaded straight into the holds of bulk carrier ships. This flow map tracks the global trade routes for those ships. Out of the roughly 1 billion tons of seaborne iron ore traded annually, about 2/3 is funneled straight from Australia and Brazil into a single nation, China. This immense geographic mismatch creates a tight geopolitical codependency. The world's largest steel producer and its major raw material suppliers are locked into a high-stakes trade relationship, where any policy shift or supply disruption immediately ripples through the global economy. To actually produce steel, that shipped ore has to be fed into a blast furnace. Because iron naturally occurs as an oxide, its iron atoms are tightly bound to oxygen atoms. Breaking that chemical bond to extract the pure liquid metal requires extreme heat and a powerful reducing agent. Historically, the industry has relied on metallurgical coal, baked into coke, to do the job. At high temperatures, the carbon from the coal forcibly strips the oxygen away from the rock. They bond together and escape the top of the furnace as a continuous plume of carbon dioxide. This chart shows the cumulative result of that reaction. Producing iron and steel accounts for 7 to 11% of all global energy-related CO2 emissions, making it one of the most carbon-intensive processes on Earth. We rely on steel for everything, from wind turbines to electric vehicles. We have to keep making it, which means the foundational chemistry of the modern industrial world has to be rewritten. The industry is starting to shift toward electric arc furnaces, which use electricity to melt down existing scrap metal without the need for coal. But scrap availability is limited. To produce fresh, primary iron cleanly, engineers are developing a technology called hydrogen-based direct reduction. This infographic shows the new chemistry. The direct reduction process feeds green hydrogen into a shaft furnace to chemically strip oxygen from the iron ore. Because the reductant is hydrogen, the byproduct is water vapor. Powered by renewable electricity, this cuts emissions by 97%. The catch is that hydrogen reduction is a highly sensitive process. To work efficiently, it requires incredibly pure, extremely high-grade iron ore pellets with almost zero impurities. That demand for purity is triggering a global resource race. State-backed consortia and mining titans are pouring billions into rare, unexploited, high-grade deposits, like the massive Simandou project in the mountains of Guinea. The nations that can secure both premium, high-grade rock and abundant, cheap, renewable electricity are positioning themselves to dominate the industrial economy of the future. Every steel beam in a city skyline anchors 3 separate stories: billions of years of deep-time geology, the intense gravity of global trade, and the total chemical overhaul of our industrial existence.